books that have nice explorations of various topics, including in physics. And there's a whole category for quantum mechanics, and so I downloaded this from the quantum mechanics section, bound states of a finite potential well. And so here, what it does is it lets me change the depth of the well. And I didn't have time to figure out exactly what the units are supposed to mean here, but the point though is just that we can make the well have different depths here. So here is a plot of the well, and with this particular depth, this is showing the even solutions. With this particular depth, notice that Z0 is such that it lies in between pi over 2 and pi. And I know you can't see this very well, but in between pi over 2 and pi would mean that there's only one intersection. And so there's only one bound state in that situation. So here it's plotting that bound state. And it's got one hump in it. The wave functions inside the well look a lot like they do for the infinite square well, except that it's no longer true that the wave function goes exactly to 0 on the ends of the well, like it does for the infinite square well. It gets close to 0, and then it dies exponentially away towards infinity on either side. So the wavelength is a little bit longer than it would be for the infinite square well. And what does that mean about the energy? Is the energy a little bit bigger or a little bit smaller than it would be for the infinite square well? Smaller, right? Because the shorter the wavelength, the higher the momentum, quote unquote, the higher the energy. So the energy is a little bit less than it would be for the corresponding state of the infinite square well here. Now if I increase the depth of the well, so I'll click on the little 8 there, I've made it 4 times deeper. Then this is for the even eigenfunctions. This is for the odd eigenfunctions, the one you're going to solve for. So here, in that case, you're going to get that instead of the intersections being with tangent y and the funky square root of z0 over z squared minus 1, it's the intersections with minus cotangent of y rather than tangent of y that you're looking for. So in this case, and I should go back because I forgot to mention that, if I go to the 2 case there, there's always an even solution. There's always at least one bound state, no matter how shallow or narrow I get, because always you're going to have an intersection with tangent of y, because tangent of y goes to 0 at y equals 0, so no matter how small z0 gets, you're going to get at least one intersection in there. So there's always at least one even bound state. But here's a situation where there's no odd bound state, because there's no intersections with minus cotangent of y. So you don't always have any odd solutions, because those are the ones that look like sines inside the well instead of cosines. And the lowest energy one would be the one that has almost one whole wavelength fitting inside the well, just like for the infinite square well. What does the first excited state, the next energy level look like? It's the one where there's one wavelength fitting inside the well, 2 humps, 2 antinodes inside the well. You follow me there? You know what I'm talking about there? So the one hump is the ground state of the infinite square well, 2 humps is the next level up in the infinite square well. And for the finite square well, the states look similar to those, except that they don't go to 0 on the ends. They go to something a little bigger than 0, and then they die away towards 0 exponentially as you approach plus and minus infinity. So the states for the finite square well look inside the well like somewhat longer wavelength versions of the infinite square well. And so, so there's a correspondence between infinite square well states and finite square well states. So the even states are the ones that look like the sinusoids inside, the cosines inside, and the odd states are the ones that look like sine waves inside here. So the lowest possible energy for an odd wave function here is one that has almost one full wavelength fitting inside the well, 2 humps. Here, there are no solutions. There's no intersection there. But when I make the well a little deeper, now I've got one even intersection, one even function intersection, and one odd function intersection. So there are two bound states, an even function, this one right here, and an odd function, this one right here. And then there are no more intersections on either graph. So for this particular depth of the well, there are two bound states. One which is odd, and one which is even. The lowest one is even. Next higher up is odd. And then if I make the well a little deeper, I move to a situation where now there are three bound states. Two even ones that look like cosines inside the well, and one odd one that looks like a sine inside the well. So here is the ground state, the lowest energy state, which is a one-hump cosine. The next higher energy up is a two-hump sinusoid inside the well. The next energy up is a three-hump cosine inside the well. So it's always one hump, two hump, three humps, and so forth, right? The next one would be four humps, and it would be even or odd. The four-hump state will be even or odd. That'll be an odd one, right? So let's make the depth 30. And sure enough, now we've picked up another odd solution. So now we've got this guy right here, the four-hump odd solution, which looks like a sinusoid in there. Notice it will be fairly different in energy from the infinite square well case, because here it's not such a good approximation that it's going to zero on the ends. And so this wavelength is noticeably longer than the four humps in the infinite square well case would be, because the four humps in the infinite square well case would have two full wavelengths sitting inside the well. This is, the wavelength here is noticeably longer than that. In other words, four wavelengths are like from here to here. If I extend this one, it'd be like that long. So four wavelengths is, or I mean, four humps. Two wavelengths is noticeably longer than the well itself is. So the wavelength here is noticeably longer than the four hump, two wavelength, infinite square well solution. So this energy is noticeably lower than the, well, I'm tired of saying it. Okay, four hump, two wavelength, infinite square well solution. Have you guys ever heard the Flying Purple People Eater song? It was a one-eyed, one-horn, flying purple people eater. So let's see. It was a four hump, two lambda, finite square well solution. I don't know, something like that. And then, well, maybe you see the pattern. So if I make it 50 now, well, now I picked up another even solution. And so now there's a five-hump even solution in there. And as I keep making the well deeper and deeper, I keep picking up new solutions. And I keep more and more. And then here these red lines show the actual energies associated with these solutions. So the ground state's a little bit above the bottom of the well. First excited state, second excited state, third excited state, fourth excited state. In this case, there is no fifth excited state because you just cannot meet the boundary conditions with any more humps inside the well. You cannot do it. Essentially, it's because, look at the energy spacings here. The next one it wants to make is up here somewhere where you're above the top of the well, and that would not be a bound state in that case. So even though we could not analytically solve for the energies, we could still get lots and lots of insight from making these graphical solutions. Questions? Okay. So now I will point the camera back towards the middle. Hello, imaginary student looking at the camera there. You have turned your head back to the blackboard where it should be now. I will zoom your eyes out. There you go. I control you. You are mine. Let's see. Lights. Camera. Action. Something like that. No. Yes. Maybe. And wake up. There we go. All right. Upsy daisy. Black screen. There we go. In case you didn't know, it says black screen. I don't know why they have that there. It's like, I guess it's just to tell you the projector's on, but that could be kind of just distracting. I did forget one. Says, you know, in the old days of transparencies, you could cover things up and only reveal things one line at a time. Now, of course, in PowerPoint, you go, you know, stuff like that, right? But I have forgotten sometimes before, so I'm like on the screen trying to hide things. It turns out not to work. All right, anyway, let's look at some limiting cases here. So we'll leave this picture up. Let's look at some limiting cases. Let's look at two of them. Let's turn the lights on the blackboard somehow. There we go. Two limiting cases. We got your wide, deep well. In this case, Z naught, which is A over H bar root 2m B naught, is going to be very large. Because both the things that make it big, large A, large B naught, are true here. So it's going to be very large. So Z naught moves out very far from the origin. And that means that the graph of Z naught over Z squared minus 1 square root moves up higher than in the sketch over there. So, why, let's kind of do that, he said, foolishly. Yeah, okay, I'll be fine. This is where my wife and me are going to go. Oh my God, oh my God, oh my God. All right. So if Z naught's way over here somewhere, then the graph is like way up here, something like that. And notice that in that case, those intersections with the tangents are going to be very nearly at pi over 2, 3 pi over 2, 5 pi over 2, and so forth. The intersections get very close to pi over 2, 3 pi over 2, 5 pi over 2, right? Does that make sense? Because this whole thing goes whee! And as I slide this thing up, the intersections get closer to those asymptote lines there. 3 over pi over 2, 3 pi over 2, 5 pi over 2, and so forth. So the intersections of tan Z and square root of Z naught over Z quantity squared minus 1 lie just below Zn equals n pi over 2 for n naught. And guess what? For the even functions, they're just below pi, 2 pi, 3 pi, and so forth. Here it's for the odd multiples, the quote-unquote half-integer multiples of pi, or the multiples of pi over 2, odd integer multiples of pi over 2. Thus, what do we want to say? Thus, square root of 2m times e plus b naught over h bar times a is approximately n pi over 2 here. Because, why because? Let's see, because this was, I had it in my head before, now I want to be sure I remember Z is L times A. And so the values where the intersections are values of Z, and L is square root of 2m E plus V naught over H bar. So all this is LA. So Z equals LA is nearly n pi over 2 in this case, because Z is LA. And so the intersections are Z is pi over 2, 3 pi over 2, 5 pi over 2. So therefore, root 2m equal all that stuff is LA, root 2m E plus V naught over H bar A is approximately n pi over 2 for n equals 1, 3, 5, 7, etc., etc. Or in other words, E plus V naught is very nearly equal to n squared pi squared H bar squared over 2m over the quantity 2a squared. Now, can anybody impress me by interpreting that expression? What were the energies of the infinite square well?
They were actually independent of their boundary terms.
What were they? They were, the energies of the infinite square well were n squared pi squared H bar squared over 2m A squared. But when we did the infinite square well, we called the whole width of the well A. Here we're calling it 2a. And E plus V naught is how far you are above the bottom of the well here, which is the same thing as we meant when we talked about the infinite square well energies. The energy in the infinite square well is, since the energy is 0 inside the well, how far you are above the energy of the well. So, the E plus V naught is energy above bottom of well. And these are infinite square well energies for a well whose width is 2a. So in other words, for a wide, deep well, the energies are nearly the same as the infinite square well energies. The exception will be when you're getting close to, eventually you get out way over here somewhere where the graph is crashing down towards E naught and the value where then the plot is equal to 0. So this breaks down for the highest allowed energies where you finally get to a region where you're back close to the horizontal axis again. But the first several n values, which could be many of them if Z naught is far enough that way over, the first several or even many n values have associated energies which are almost exactly the same as for the infinite square well. Well, that kind of makes sense. In other words, if I have a finite square well, which is really very deep, and the particle has not too much energy, then it almost looks like an infinite square well to that particle. And so therefore it makes sense that the energy is almost the same as it would be for the infinite square well. So in that situation, if I have like, well, out here, because there's a huge energy difference between 0 and the energy of the level, the exponential decay is extremely rapid outside the well. So you'll get a situation where, okay, the wave function doesn't exactly go to 0 right on the boundary, but man, it's close. It's hard to even tell the difference between that and 0 when you're right on the boundary for the first several energy levels. And so they practically look like infinite square well energies. They practically have the same value as infinite square well wave functions. They practically have the same energies as infinite square well wave functions. And notice here, when we plot the wave functions higher and higher like this, what we're doing is they're really all fluctuating about 0, but we just plot them higher and higher just for convenience to kind of separate them. But really, we're kind of shifting along. This is x equals 0 for this energy. This is x equals 0 for this energy, and so on and so forth. We're just drawing funny to keep them from all sitting on top of one another. So does that make sense, not make sense? Questions, including, can you say that again, because I don't really know what you're trying to say. Remember, the hill you're talking about is perfectly good question. One of the best questions.
So arguably, at one point, if we get a high enough energy state, it will begin to look less like the infinite square well, more like the particle.
Yeah, and so the idea there is when you're, in other words, eventually you get an energy which is way up here. When you're getting energies which are close to the top of the well, which are close to zero, which are close to the top of the well, because we define things so that the top of the well is zero, the bottom of the well is minus V naught. As the energy starts approaching zero, as the energy starts getting close to being V naught above the bottom of the well, then it's no longer a good approximation that it's an infinite square well wave function or an infinite square well energy. Then it becomes noticeably different from it, and a bit lower than the infinite square well energy would be for the same number of humps in the wave function. So that's the wide deep well. Wide deep well looks like an infinite square well if you're pretty far inside of it. It's like reality too. In other words, okay, what's the difference in practical terms between falling into a bottomless pit, and falling into a pit that's 10 miles deep? Well, if you're at the bottom of that pit, it doesn't make that much difference to you, which of the two situations you're in. And that's
technically you'll die when you hit the bottom of a 10-mile pit, but you won't when if it's the bottomless one because it's in the bottom. Oh, right.
okay. So that was one case. Gosh, what will the other case we look at be instead of the wide deep well? Yeah, narrow and shallow sounds like a good idea. So let's look at the narrow shallow well. We've already looked at it in the Mathematica plot. You already know what's going to happen. If it's shallow and narrow enough, Z moves over into the range between 0 and pi, and then you've only got one intersection in that case. So as Z naught diminishes, number of intersections decreases. So number of bound states decreases. When Z naught drops below pi, there is only one intersection and therefore one bound state. Now, my arm's tired. Only one intersection and thus one bound state. But there always is at least one, because no matter how small Z naught gets, you're always going to hit the tan function in between 0 and pi over 2. So there's always one intersection for the even solutions. For the odd solutions, not so. For the odd solutions, you get minus cotangent, which looks different, and you cannot have any intersections in that case. So here's a question. How many bound states for the delta well? 1. So is it wide and deep or narrow and shallow? Yeah, it's narrow and shallow. Let's try to justify that. Now that we have done this treatment, we can decide what does Z naught do for the delta well? So, can I erase this? Is that, everybody got this? No? I see people still writing. So. Okay. I'll call my, well actually, at this point I think I can erase over here. I'll just erase the, yeah. Okay. Delta function well. Remember that for that one we said that v of x was equal to minus alpha delta of x, and that we could generate that as being the limit of finite square wells which have width A and depth minus alpha over A. So that as A goes to 0, the well becomes deeper and deeper. And well, there we have it basically. So width A and depth minus alpha over A. Because if alpha were 1, this is going to minus delta function. But, because you want the area to be 1 in that case. Here we want the area to go to minus alpha. So width A times height minus alpha over A gives area minus alpha for this well. And then let A go to 0, it gets deeper and deeper such that it's a spike which has area minus alpha there. So this is our model of what the delta well represents. Think of this getting narrower and narrower. Let A go to 0, so the depth of the well minus alpha over A gets deeper and deeper and deeper minus alpha over A. Okay, so for any one value of A, what is Z naught here? So Z naught, so in other words here, we're setting V naught being to what in this situation? The depth of the well is V naught equals alpha over A. The depth of the well is alpha over A. The depth of the well is alpha over A for any given value of A that we're looking at here. So Z naught is A over H bar root 2m V naught but V naught is alpha over A. So this looks like root 2m over H bar, and then A over root A is what? Root A, right? So root alpha A. For any one of these wells in this series, Z naught is root 2m over H bar times root alpha A. So what is Z naught doing as A goes to 0? Is it blowing up or is it vanishing? It's vanishing. As A goes to 0, Z naught is going to 0 here, so that's why the delta well is a shallow well. It's a shallow well because Z naught is what decides whether a well is wide or shallow or narrow. And here, as the well width is going to 0, this is turning into a shallow type of well, narrow shallow. And that's why there's only one bound state. Because that's the regime we're in. We're in a one bound state regime there, even though it's not immediately obvious because, oh my gosh, it's narrow, right? But it's also infinitely deep. Yes, but overall, we're in the Z naught going to 0 regime because of the fact that the width of the well is going like A, but the depth of the well is going like root A. And so the width is diminishing faster than the depth is increasing as A goes to 0. And so therefore, the width wins. The narrowness of the delta well overwhelms the depth of the delta well and puts us into the regime where Z naught is going to 0, in other words. So that's why there's only one bound state, or that limit. Question? Oh, okay, so now, any questions? Oh, good, because see, now we're going to talk about positive energy solutions. And just like for the delta well, we're going to say, okay, there's no quantization here. You can have any energy you like. And the ones that are interesting are the ones that represent scattering. And so I was having a conversation with my colleagues and about to come over here, and then I realized that I needed to switch mental gears to quantum mechanics. And then I realized that, in fact, what I needed to do is to become scatterbrained. Okay, so let's be scatterbrained here. Let's talk about scattering from the finite square law. Scattering states. The ones with E greater than 0. We're not bound. We're free. This time, we don't want to limit ourselves to even and odd solutions because scattering problems are inherently asymmetric. Particle comes in, partly reflects, partly transmits. So there's two waves on one side, incident wave and reflected wave, and only one wave on the other side, scattered wave. And not all the solutions have that form, but there are solutions that have that form, and those are the ones that are interesting to us because those are the ones that represent scattering from the well. So on that physical ground, we're looking for solutions which consist of an incoming wave, a reflected wave, and an outgoing wave. So this time we don't restrict ourselves. We could, but we don't want to. We don't want to limit ourselves to even or odd solutions, since scattering problems are inherently asymmetric. So we'll start with x is less than minus a. Minus h bar squared over 2m d squared psi dx squared plus v psi. What's v for x less than minus a? 0. The way we've drawn the well is that it is 0 outside minus a and a for the potential, and equal to minus v naught in between minus a and a. So for x less than minus a, the potential is 0. So minus h bar squared over 2m d squared psi dx squared plus 0 psi is equal to e psi. Here e is greater than 0. So this says d squared psi dx squared is equal to minus, now we'll call it good old k squared, minus k squared psi, where k, by definition, is root 2m e over h bar, real and positive. Because now e is greater than 0, so root 2me is greater than 0. Therefore, is this tricky or XD? It's tricky. It's tricky. So we could make psi cosine kx, sine kx, but we don't want to, because we want to represent traveling wave solutions here. And so when the time dependence, remember, is always e to the minus I et over h bar, or in other words, e to the minus I omega t, I need to make that combined with an e to the ikx or an e to the minus ikx to make traveling exponential trigonometric solutions. So we'll use trig functions, but we'll use the trig functions which are complex exponentials, combinations of cosine plus I sine. So we're going to say psi is equal to a e to the ikx plus b e to the minus ikx for x is less than minus a. Noting that, so then capital psi will be equal to a e to the I kx minus omega t plus b e to the minus I kx plus omega t. So we're going to have a right traveling wave and a left traveling wave. So we've got an incoming incident wave, a back-going reflected wave when we throw in the time dependence. So we've got that in the back of our minds when we choose this as the space part of the wave function. Is there any kind of blowing up in infinity that we need to worry about here? Does either of these terms blow up as x goes to minus infinity? Nope, they just go wiggle, 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 wiggle. Actually, they're complex exponentials, so they kind of go wong, wong, wong. They're rotating phasors, so they do this as they go around. Jet engines screws or something. Oh, that's the trees are back there. All right. No worries, mate. About blowing up as x goes to minus infinity. Keep them both. So now let's look on the other side. X greater than a. What's the Schrodinger equation on that side? It's exactly the same, because the potential is 0 there as well. Same Shrek as for x less than minus a. So we could say psi was equal to, which one do they toss there? Psi was equal to, psi could be f e to the I kx plus g e to the minus I kx, but we want this to represent only a transmitted wave. So we want the right-going wave or the left-going wave? A right-going wave. Yeah, the one that's heading off this way, because x greater than a, I want the wave to be moving away from the well. So on that ground, I throw away the reflected wave, or at least I throw away the particles that are coming in from the other direction just to contaminate our experiment. And I only keep this term. So I only keep the e to the ikx term. I set g equal to 0 just because I want to. not saying that the solution has to look like this. We're saying we want it to look like this. We only want a transmitted wave, so we declare that G is equal to 0. So we want psi just as f e to the I kx for x greater than a. Meanwhile, back at Finite Square Well Ranch, inside the well, what's the Schrodinger equation look like? So minus a is less than x is less than a, minus h bar squared over 2m d squared psi dx squared. What? Plus v psi, but v is equal to minus v naught, so minus v naught psi equals e psi, which looks in form just like we had before when we were looking for bound states. But in this case, then, it's going to be that we've got, well, actually it looks just like it did before. It's still just relative to the bottom of the well, but we're just higher up. So d squared psi dx squared is equal to minus L squared psi, where L is just like we had before, root 2m E plus V naught over H bar, where E plus V naught is the energy relative to the bottom of the well inside there. And just as for bound states. And so here we're going to get tricky with it. And we could use exponentials again, and some treatments do that, but we'll make them sine and cosine, just because it turns out to be more convenient. If you do it both ways, this works out to be a tad more convenient. So c sine Lx plus d cosine Lx for minus a is less than x is less than a. So it's pretty much time to stop, but just to set the stage for our glorious class on Thursday, which we wouldn't even want to not have, our job will be to have fun with the boundary conditions at the two locations. And here we've got constants C and D, A and B, and F. So we've got 5 amplitudes there. And 4 boundary conditions, because there's continuity of psi at minus A and plus A, continuity of psi dx at minus a and plus a. So 4 equations and 5 unknowns. Normally, normalization would come in, but here we can't normalize these wave functions. They have constant squared amplitude as you go to plus and minus infinity. So what we'll do is we'll just arbitrarily declare one of them to be, say, 1, and then solve for the other ones in terms of that, or else you just say, okay, we'll solve for everything else in terms of a. And that's what we're going to do, is we'll solve for everything else in terms of the incoming amplitude A, and then ratios will represent the transmitted and reflection coefficients. And we'll declare what you're going to get when you actually do it yourself in the homework problem. By doing problem such and such. Yes?
So are you used to use sine and cosine instead of complex exponentials there?
Yeah, it just works out to be a little easier, that's all. You could use complex exponentials. But it turns out that inside the well you get a standing wave anyway, because you're getting interference between the reflections coming off the boundaries. And so it's okay to put that in there. It's a standing wave anyway, so it works out to be just a little easier. But you could do it with complex exponentials too. No problem. Okay. Any questions? Is it time to go? Yes. I have the answers there. All right, so if you have questions about quantum mechanics, you know where to go. And send me email, I'll be responsive to email. Find me in my office hours, all those kinds of things. I will be around in the lab for Physics 115 tomorrow afternoon from 1:10 till 4 is over. Feel free to come bother me there. You just have to be willing to let students
go shut this.
Can you go to the
Yes, we just-
You go.
Oh, people shout.
Yeah, because I have I don't want to carry it around. See, now this is, I know I can see What?
There's hardly anyone in the unit other than us. Us as in you, me, Michelle.
Yeah, I mean, I eventually might just leave my stuff in there in the station.
That's what I do. I just leave my stuff in there.
Oh.
Oh, this the Jackson time? No, we're planning to move the lounge into the other room.
Which one?
The one next to it because it's bigger.
What's the hell? I forgot to send it out.
Was that-
And then it's in the-
Yeah, it's still taping, that's right. Or still writing to memory. It's got tape in it, so.
Yes, right into the fire.
Yes. And so I say good night.